Problem number 3. A. Calculate the bending stresses in the beam shown by using the transformed area method. Fc prime, or strength of concrete, is 3000 psi, N, or modular ratio, is 9, and M is 70 foot-kip. Letter B. Determine the allowable resisting moment of the beam if the allowable stresses are Fc, or stress in concrete, allowable is 1350 psi, and Fs, or allowable stress in steel, is 20,000 psi. Let us look at the figure and see what are the given data. We are given the beam dimensions. We have the beam width designated as B. This is 12 inches. We are also given the height of the beam, which is 20 inches here. Then we are given D. D is effective depth. Effective depth means it is the distance from the outermost compression fiber right here to the centroid of your steel, and this one is given to be 17 inches. Fc prime is 3000 psi. Then we have modular ratio of 9. It means to say that steel is 9 times stronger than concrete. Alright, steel is 9 times stronger than concrete in this problem. Then we have AS, or area of steel, that is 3 square inches. Now we are lucky to be given the area already, but in case we are not given the area but only the rebar number, we can still solve for the area. Now we know that rebar is circular in diameter, so the formula is pi d squared over 4. And what is our diameter? That will be 9 always over 8. All diameters should be divided by 8, whether it's 5, 6, 7, 8, 9, 10, 11, so on and so forth. Everything shall be divided by 8. Then we square it and divide it by 4. And then multiply it by the quantity. We see here 3 pieces. So times 3. And that is your area of steel. And if you calculate, that will be 3 square inches. Okay? So just in case if the rebar area is not given. Then moment, we are given the value of moment to be 70 foot-kip, and we are given allowable stresses for concrete, which is 1350, and allowable stress for steel, which is 20,000 psi. Alright, so the approach in solving this problem is first to locate the neutral axis. Now, if I may illustrate, the beam profile would look something like this sideways. I'm trying to exaggerate the bending here. So if the beam, a certain beam is loaded as shown, it will have this bending, and if this is your neutral axis, everything below the neutral axis will be tension, and everything above will be compression. Now, if we try to recall, we can say that concrete is very weak in tension, hence we will discard the tension strength of concrete. So everything below, we will only consider the steel component here. The steel component. And everything above the neutral axis, we will only consider concrete. Okay? So if we try to illustrate in this beam section, if we assume this one to be our neutral axis, everything above will be compression, and then below, which is the steel, that will be used for tension. Alright, so first we designate this one, let's say X, because we still don't know the location of the neutral axis. Now, to solve for that location, we take moments about the neutral axis. Take moments about the neutral axis. Okay, because the moment is 0 at the neutral axis because it's neither compression nor tension. So if we take moments, we need to get the distance from the centroid of that certain area to the neutral axis. So for concrete, the location of the centroid is at x over 2. And for steel, this one is D. So let's say D minus this value here, which is x. So D minus x. So to take moments about the neutral axis, first we account for the area. Area is B times x. Okay, this is B and this is x. And then multiply by the moment arm, which is x over 2. Okay? And that will be equal to the area of steel. But remember, steel in this problem is 9 times stronger than concrete. So we need to place here the N, or the modular ratio. And then the moment arm will be from the neutral axis to the centroid of this steel. That will be D minus x. Okay? Then, to simplify that one, because we need to solve this equation and find x, we can transfer to the other side and make it a quadratic equation. So that will be bx squared over 2. And then we distribute the ASN or NAS here. We distribute. And then transfer to the other side. So this one is positive AN times D. So that will become negative. So I will just rearrange N AS D. Alright? Then, this one is negative, and then you transfer to the other side, that will be positive. That will be N AS X. That's equal to 0. And to make it, to format it like a real quadratic equation, so B x squared over 2 plus N AS X minus N AS D, and that's equal to 0. So we have x squared, then x, and then the constant. Okay? So that is why this is converted into this formula. Now, to solve a quadratic equation, we use the quadratic formula. And what is the quadratic formula? Quadratic formula is minus b plus and minus the square root of b squared minus 4ac all over twice of a. So we can solve the quadratic equation using this quadratic formula. Okay? So all we have to do is identify what is your b, identify what is your a, identify what is your c. Okay? Now, in this equation here, a is this. This will be your a. And this will be your b. That will be your B. And this one will be your C. Alright? So here you can see that A is B over 2. Your B is NAS. And your C is, we include the negative because this is plus negative. So plus negative. So negative NAS times D. Negative NAS times D. Okay? So with all the three that are already solved, we can solve the quadratic equation. So what is our B over 2? B over 2 is simply 12 over 2 or 6. So that is 6 inches. And our B is NAS. N is 9 and AS is 3. So 9 times 3, that will be 27 inches. And C is negative NASD. So our negative N is negative 9, AS is 3, and our D is 17. So 9 times 3 times 17, that will be negative 459. Okay? And then after that, you plug in these three values in the quadratic equation. So plug in these three values here to this quadratic equation or this, and you will generate an answer, which is this answer, 6.78 inches. And that will be the value of your X. Okay? So that is how to locate the neutral axis. Now, after locating the neutral axis, the next step is to solve for I. Okay? Solve for I. Now, we know that I, for the entire section, we use the transfer formula for I, wherein IG or I is equal to IO plus AD squared, where D is the distance between the neutral axis and the centroid of that particular area. And we have two areas here, area for concrete and area for steel. So let's account first for concrete. This one is rectangular in nature. So therefore, the formula for IO there is just simply BH cubed over 12, or equal to B, which is 12, and H is this one, 6.78. 6.78 cubed over 12. And you will generate this answer. And area, of course, area is just B times 6.78 or B times X. So we have that answer. And our D is simply X over 2. The distance from the centroid of this area to the neutral axis. So that will be D over 2. That will be 3.39. And the IO plus AD squared, you add this one, and then AD, A here, and then D squared, you will generate this answer. Okay? And then, since we have concrete and steel, this will be a summation. Okay? Summation of concrete and steel. So for the steel, since this is a very small area compared to the concrete area, we discard the IO here. We discard the IO. But for the area, we still account for it. That will be NAS. Okay, because we have the modular ratio comparing concrete to steel. So NAS, that will be 3 times 9 or 27. Now going back here, this IO is not calculated because we deemed the steel to have zero stiffness. And if you have zero stiffness, then there's no need to calculate for the IO. Okay, because I is a component of the stiffness of a certain material. Okay, then for D, the distance between the centroid here to the neutral axis, that will be D minus X. So simply 17 minus 6.78. That will be 10.22. And IO plus AD squared, we don't have IO, so simply AD squared, we can generate this value. And then adding the 2 here, we can solve for the I of the entire section, which is 4066.77 inches to the fourth. Okay, so what we were able to find out is the location of the neutral axis plus the I, and we are now ready to solve for the bending stresses in concrete and the bending stresses in steel. Okay, and by the way, our distance for concrete, the Y for concrete and steel are the following respectively. This one is X here, and this one is D minus X right here. So for the bending stresses, we always try to recall FB is MC over I. Okay, now here if we convert it to our particular problem, that will be M, and our C is Y concrete over I for concrete, and for steel, our Y here is the Y for steel, and then we multiply it with the modular ratio, which is 9. Okay, so to solve that, simply substitute the moment value, which is 70, but first convert it to inches and pounds. Okay, so to multiply it, to convert it to pounds, multiply it by 1000, and to convert it to inches, multiply it by 12. So multiply 70 by 12,000. Okay, so 12,000 times 6.78 divided by I, you will generate this answer. Okay, and for steel, N, which is 9, times the moment, which is 70, and multiply it by 12,000, then multiply by the Y of steel, which is 10.22, and divide it by I, and you will generate this answer. Okay, so you can clearly see here that the steel is the one being stressed so much when the beam is bended, because this one will hold a lot of tension stresses and above will have compression stresses. Okay, now for question B, determine the allowable resisting moment of the beam if the allowable stresses are FC prime or FC equal to 1350 and Fs is 20,000. Okay, so manipulating this formula, we can have the allowable moment. So moment here will be F times I over C, and F now will be your F allowable, I will be the I of the entire section, and C will depend on the question whether it's steel or concrete. So it can either be concrete or steel. So for moment in concrete allowable, that will be in concrete allowable or 1350 psi times I, which is this, over Y concrete. And Y concrete is 6.78. So plugging in the values, you can generate this answer in terms of pound, inch, and then divide it by 12,000. Okay, to convert it to foot kip. Next is for the steel. F in steel allowable, which is 20,000, times I, which is 40,000, divided by, don't forget the N here. Now always remember to include the modular ratio, and then Y in steel, which is 10.22 right here. And you will generate this value if you divide it by 12,000. Okay, to convert it to foot kip. Alright, thank you so much.